Hey, Dr. Co. Let's talk about buoyancy. So we've got our log has a length, it's got a radius, and the surface of the water has a height to the top. Buoyancy is equal to, buoyancy force is equal to the weight of the fluid displaced. So we could say that the weight of the fluid, which is water in this case, is equal to the weight of the log, because the only two forces acting in this scenario are the force of gravity for the log and the force of buoyancy. And that's equal to this weight. So that works out really well. The weight of the weight is equal to mass times gravity. Density is equal to mass over volume. So we can get weight is equal to density times volume times gravity. Volume is equal to area times length. So we get weight is equal to density times area times length times gravity. For the water, we have the density of water is equal, or times the cross-sectional area times length to get the volume of the water displaced times gravity. Then we have that's equal to the density of the log times pi r squared, that surface, times the length to get the volume of the log. We can simplify these terms. Now we have the density of the water times the cross-sectional area is equal to the density of the log times that area. Now we can get these terms into the specific gravity, which is what we want. We know what R is, but we need to find the area right here. So we're gonna draw another area to better visualize this. We still have H. That would be R for radius. That means this is R minus H. We're going to call this distance X, and we're going to call this angle theta. So we're going to first solve for the area of the triangle, which is this section right here. That would be equal to 1/2 base times height. The base would be 2 times X, because 2 times that distance, and the height would be R minus H. We need to solve for X, so we'll do the Pythagorean theorem. R minus H squared plus X squared is equal to R squared. Solving for X, we get square root of 2RH minus H squared. And substituting that in, we get the area of the triangle is equal to, and canceling some terms out, square root of 2RH minus H squared times R minus H. The area of the slice, which would be this entire section right here, would be 1/2 R squared times the angle in which you're slicing. In this case, it'd be 2 times theta, because there are 2 thetas right here for which we want to find the area. We can cancel those out, and we need to solve for theta. Using trig, we can say the cosine of theta is equal to R minus H over R, and theta is equal to arc cosine R minus H over R. Substituting that back, we have the area of the slice is equal to R squared arc cos R minus H over R. Now we want to find the area of the hump, and I call it that because it looks like a hump. That's this area up top. That's equal to the area of the slice minus the area of the triangle, which is equal to R squared arc cosine, R minus H over R, minus the square root 2RH minus H squared times R minus H. Now that we have this, we need to find the opposite of that area, which is the cross-sectional area under the water. That would be our A, which is equal to pi r squared minus the area of the hump. So our A is equal to pi r squared minus r squared arc cos r minus h over r minus the square root 2rh minus h squared r minus h. Now that we have this area, we can substitute it back into our density equation, and let's rework some of this right now. We'll say the density of the log over the density of the water, moving that to the other side, is equal to the specific gravity of the log, because it is, time, and then that's equal to 1 over pi r squared, because we move this to the other side with the area, and that's multiplying by this term right here, times area. Now we'll simplify this multiplying by the area. This will become 1, and that'll be minus 1 over pi with this term. That'll still be arc cosine. Simplifying this term, we get 1 minus h over r. And this term, we're going to do something funky with it. These two terms. We're going to multiply the inside by r squared over r squared. And you'll see why. A little too long. And we're going to multiply this term by r over r, because we can. We're going to pull this r out of there, and we're going to pull this r squared out. So we have r times r, which cancels out with this r squared. Then we're going to simplify this inside term to get 2 times r, or h over r, minus h squared, or h over r squared. That's under the square root, and because we pulled that term out, this will simplify to 1 minus h over r. This is 1 over pi, and copying down the rest of the expression, we have this equation, this expression. Now, finally, we have the specific gravity of the log in terms of h over r. Now we're going to move on to the coding section. Now we can start coding. First, I'm going to import some tools to help us out in the calculation. First, I'm going to import numpy for all of our helpful calculations. And I'm going to import root scalar. That'll help us get our final value later on. I'm also going to import this to help with the graphs that I'm going to make, because I want to be able to see what my value might be before I move on. Now I'm going to define my variables. I'm going to make HR an array from 0 to 1. It's going to be made up of 10 values. And I'm also going to import my expression for the specific gravity, which I solved for earlier. So if this is correct, everything looks pretty correct in there. Now I'm going to go to the figure so I can see expected value or what it should be close to. Our x is going to be the HR relationship, and our y is going to be the specific gravity. So if we look at this, this is our HR relationship, this is our specific gravity. So with the specific gravity of 0.8, that'll give us a value for the HR relationship of about 0.5. So let's keep going in the coding to see if this is true. We're going to define the function with respect to HR. We're going to return this value. It's going to be the specific gravity expression minus 0.8, so we can get the value expected at 0.8. And we're going to, but first we need to change the results from the array using root scalar. This will give us a value. Function. And our result is this, 0.508, which is close to what we expected of the 0.5. Thank you for watching me solve the expression and watching me code this in Collaboratory. I'll see you on Monday, Dr. Co.